Next, we look at number 26 involving differentials. So we have the function y equals radical x, and we want to find the differential dy. So again, keep in mind dy is f prime of x times dx. So we need f prime of x in this case. So f of x is x to the 1/2, just using our regular derivative rules. F prime of x is 1/2 x to the negative 1/2. Or we can write that 1 over 2 radical x. So the differential dy is just 1 over 2 radical x, f prime of x, times dx. And that's all there is to it. Now let's evaluate the dy and also delta y if x equals 1 and dx, also known as delta x, so those two are always the same, if that's equal to 1. So in other words, we're starting at x equal 1, and then we're moving 1 to the right from there to x equal 2. Okay, so dy we know is 1 over 2 radical x times dx. That's what we just found in part A. So we're going to evaluate that when x is 1 and when dx is 1, and that gives us 1/2. Okay, so 1/2, or if you prefer 0.5, this is the estimated change, that's what dy is doing, in radical x when x increases from 1 to 2. Now, delta y, we could also write that as delta f. That's f of x plus delta x minus f of x. So that's the actual change in the function value. So that would be f of 2 minus f of 1. Now the square root of 2 is about, so that's radical 2 minus radical 1. So the square root of 2 is about 1.414. Square root of 1 is 1, so about 0.414. Okay, so that's the actual change. Again, with rounding error. I mean, that's the correct amount of change to 3 decimal places. That's the actual change in radical x when x increases from 1 to 2. And again, you might be saying to yourself, I don't understand why we have to do this. The calculator can tell us how much y changes when we go from radical 1 to radical 2, but again, your calculator is actually using an estimation underneath. Okay, now part C wants us to sketch a diagram, and I have some pre-made stuff on here. And I try to follow the book in making the tangent line kind of a pinkish color, calling that L of x for linearization, and the function y equal radical x in blue. And I drew 2 separate graphs only because it gets too crowded to try to put it all on one thing. Okay, so when we move from x equal 1 to x equal 2, right, that is dx or delta x equaling 1. That's a distance of 1. Now, dy is the change in the tangent line. So we go from the point 1, 1 to the point 2. If we were on the tangent line, we'd be at 1.5. And so that difference from y equal 1 to y equal 1.5 is our dy of 1/2. Right, so up above we calculated dy to be 1/2. That is how much the tangent line changes. So, but dy is the approximate change in f of x, in this case radical x, when the x increases from 1 to 2. Okay, it's the actual change in the tangent line when x increases from 1 to 2. And we're calling the tangent line L of x for linearization. Now, on the right-hand side, I'm going to make the delta y. Right, again, they can both go on the same graph. I just thought it would be too crowded. So here again, we have x increasing from 1 to 2, so that means our delta x, our dx, is 1, an increase of 1 to go from 1 to 2. And then we're looking at how much change do we have in the actual function, and that is delta y, right, which again was about 0.414. It's not exact because we rounded that number. It goes on with many more decimal places. Okay, so the delta y is the actual change in the function when the x increases from 1 to 2. And we use the tangent line to approximate that change. Now, also, I just want to make a little note. The estimate dy is an overestimate, right? The estimated amount of change in f of x. That's my dog chasing the cat, if you could hear that. Sorry about that. That estimated change is an overestimate for how much f of x actually did change, 0.414.